Welcome to this explainer. We live in an era where humanity generates petabytes of data literally every single day. Yet when you type some vague, half-formed thought into a search bar, you expect the exact answer back in milliseconds. No pressure, right? If you've ever wondered how a database takes that vague query and just magically pulls the right answer from a sea of billions of records, well, you are in the exact right place. Today, we're popping the hood on modern data systems. We're going to trace this fascinating journey from simple, rigid lookups all the way up to AI-driven semantic searches, exploring the mathematical architecture that makes our digital lives possible.
Here is our roadmap for today. We'll start with the limits of simple indexes, move into multidimensional indexes, explore full-text search, dive deep into vector embeddings, and finally, look at the future of retrieval.
Section 1. The limits of simple indexes.
So, how do you search for meaning? That is the core question we're solving today. But before we can search for abstract meaning, we kind of have to look at how we search for simple facts. When you ask a database to store data so you can look it up later, it uses an index. Basically, it's an additional data structure derived from the primary data. The most common one you'll run into is a B-tree, which sorts data sequentially. Now, adding an index usually speeds up your read queries tremendously, but, and here's the catch, it consumes disk space and actually slows down your writes. Why? Because the index has to be reorganized and updated every single time new data is written. So databases force us to be strategic. A B-tree is incredibly efficient because it sorts data linearly, letting the database jump straight to a specific value without scanning every single row in the table. It is literally the foundation of digital memory. But what happens when linearity just isn't enough? That is exactly where traditional structures start to break down, and where database engineers have had to get incredibly creative.
Let's look at a classic example. Historically, the most common way we handled searching across multiple columns was through a concatenated index. Think of this exactly like an old-fashioned paper phone book. It's structured by last name and then by first name. Because of this strict sort order, you can easily find all the people with a particular last name. Super fast. But that exact same index is completely useless if you only have a first name. The first names are scattered randomly within those sorted last names. This entirely breaks down when you need to find, say, a restaurant within a specific map square based on both latitude and longitude. A standard B-tree index can give you all restaurants in a range of latitudes, sure, or all restaurants in a range of longitudes, but it absolutely cannot do both simultaneously. If you try, the database would have to find all the restaurants matching the latitude and then computationally disastrously scan through every single one of those results sequentially just to filter out the ones that don't match the longitude. For a global map application, no way. That kind of sequential scanning is impossibly slow.
Which brings us to Section 2, Multidimensional Indexes. When the data you're searching for relies on multiple properties intersecting all at once, like our map problem, we have to completely rethink the architecture. Instead of a linear list like our phone book, databases use specialized spatial indexes. Things like R-trees or BKD trees, which literally divide up physical space. R-trees work by grouping nearby data points together and wrapping them in what are called bounding boxes. And then, those boxes are wrapped in larger bounding boxes, creating this whole hierarchy of nested rectangles. It's kind of like Russian nesting dolls. This allows a database to simultaneously query both coordinates by instantly eliminating any bounding box that doesn't overlap with your search area. And it's not just for geography. Imagine an e-commerce website using a three-dimensional index on red, green, and blue to let you efficiently search for products within a certain range of colors. Or think about a weather database using a two-dimensional index to search for observations during a specific year where the temperature was exactly between 25 and 30 degrees Celsius. Without multidimensional spatial grouping, you'd just be stuck scanning millions of irrelevant records one by one.
Section 3. Full-text search.
Okay, let's expand our horizons. Let's move from a two-dimensional map to a world where every single word becomes a dimension. Welcome to the realm of full-text search. This is where we want to find keywords that might appear absolutely anywhere within a document. At its core, you can think of full-text search as just another kind of multidimensional query, but one with a massive number of dimensions. Consider this. An English dictionary contains roughly 170,000 words. In this system, every potential word or term is a distinct dimension. If you represent this as a matrix, it is incredibly sparse. It's mostly full of zeros, because obviously no single document contains all 170,000 words. The data structure that makes navigating this beast possible is called an inverted index. It's a key-value structure where the key is the term itself and the value is what's called a postings list. And that's really just a list of numerical IDs for all the documents that happen to contain that specific term.
Now, if those document IDs are sequential numbers, that postings list can be represented as a sparse bitmap. And let me tell you, this is incredibly efficient for a computer CPU to process. Finding documents that contain both the word red and the word apples is literally as simple as loading the two bitmaps into memory and efficiently computing their bitwise AND operation. It instantly identifies the IDs where both words appear. Boom, done. But search engines like Lucene don't just stop at exact matches, because, well, we humans make typos constantly. To handle this, systems transform their indexes using something called a Levenshtein automaton. This is a mathematical way to calculate edit distance. It's literally counting how many letters you have to change to turn your misspelled query, like APPLZ, into the correctly spelled apples. The automaton acts as this highly efficient state machine that scans the inverted index, pulling back any term that sits within a mathematical distance of 1 or 2 edits. It ensures you find your target, even if a letter was added, removed, or completely replaced. It's a total game changer.
Section 4. Vector Embeddings.
Let's move to the climax of our journey, searching for intent when the exact words aren't even used. This is semantic search, and it is a massive, massive leap forward. Semantic search attempts to understand document concepts and user intentions way beyond just raw keywords. This is how a customer help center knows that your typed query for canceling your subscription should perfectly match a highly relevant document titled Terminate Contract, even though those two phrases share literally 0 primary keywords. To achieve this kind of magic, AI embedding models train on billions of parameters. They read massive text corpora to group words that frequently appear in similar contexts. Through this training, they translate a text document into a vector embedding. A vector embedding is simply a list of floating point values that represents a specific point in an abstract, multidimensional space of meaning.
Consider a raw floating point array like the numbers you see here. In a basic three-dimensional space, an embedding for the concept of agriculture might be located at the coordinates 0.38, 0.83, 0.41. A page about vegetables would sit mathematically very close to it. Perhaps it's 0.36, 0.64, 0.67. But a completely unrelated page about, say, database star schemas would be comparatively far away, located maybe at 0.85, 0.10, negative 0.52. Now, in reality, modern embedding models use much larger vectors, often containing well over 1,000 numbers, representing 1,000 abstract dimensions. In a 1,000-dimensional space, human comprehension of what each individual coordinate means is completely impossible. But here's the secret. We don't actually need to try to understand what the individual numbers mean. They just point to a mathematical location. The relative proximity of these coordinates is what holds all the magic.
So to figure out if two complex concepts mean the same thing, the search engine literally measures the mathematical distance between their numerical arrays. It relies on distance functions like cosine similarity, which measures the angle between two vectors, or Euclidean distance, which measures the straight-line distance between 2 points in space. To visualize cosine similarity, just imagine drawing 2 lines outward from a center origin point. If both lines point in the exact same direction, the angle between them is 0. In cosine similarity, an angle of 0 means their underlying meaning is virtually identical. This is absolutely brilliant because it purely evaluates the angle of the direction, making the comparison highly accurate, regardless of whether one document is a single sentence or a massive 10-page article. When you submit a query, the model generates a vector for your sentence, and then the database just has to find the closest matching document vectors in that multidimensional space.
But of course, there's a catch. Because traditional spatial indexes like R-trees fail completely when faced with thousands of dimensions, we have to rely on specialized structures. Enter the Hierarchical Navigable Small World Index, or HNSW. HNSW maintains multiple layers of the vector space represented as connected graphs. A query begins at the topmost layer. This layer is heavily thinned out and very sparse, containing only a few key nodes. The system locates the nearest vector in that sparse layer and then drops down to that exact same node in the layer below it. From there, it traverses the connections in that slightly more crowded layer to find an even closer match, drops down again, and repeats the process. Think of it exactly like zooming in on a digital map. You start by finding the right country on a global view, zoom in to find the right city, and finally zoom in to locate the specific street. Dropping through these layers of connected graphs is an incredibly rapid way to find an approximate match among millions of high-dimensional vectors.
Now, when an engineering team chooses a vector index,
There's a strict trade-off between performance and accuracy, and it's heavily driven by real-world stakes. A flat index compares your query to every single vector in the database. It is 100% exact, but terribly, terribly slow. This is perfect for a highly critical small medical database where you absolutely cannot miss a single matching record. But for searching hundreds of millions of vectors in real time, we must use approximate indexes. An inverted file, or IVF index, partitions the space into clusters around center points called centroids, checking only a certain number of surrounding probes. It's significantly faster, but it might miss the absolute perfect match if that match happens to sit just across a partition boundary. And then we have HNSW, the layer traversing graph structure we just explored, which is generally the fastest available option today. For something like a global web search, securing sub-second responses using HNSW or IVF is the only viable path, even if it means accepting a 99% accuracy rate instead of 100%.
Section 5. The future of retrieval.
Every single time you search for something today, you are triggering a massive cascade of multidimensional geometry. From a spatial archery finding the nearest coffee shop on your map to an inverted index using bitwise operations to instantly filter millions of full-text documents, all the way to an AI embedding model predicting your exact intent by measuring the cosine similarity of a 1,000-dimensional vector. These invisible architectures have moved us from strict, rigid columns of text to incredibly fluid landscapes of mathematical meaning. They are quietly, rapidly, and brilliantly organizing the world's information behind the scenes. As these embedding models grow to tens of thousands of dimensions, parsing nuanced concepts we don't even have exact words for yet, the question isn't just how we search for information, but how this invisible architecture will eventually redefine what it means to know something. Are we still searching the data, or is the data starting to understand us?